Write the whole thing and say yes, overwrite. So now we are all cool. Now we are cool again. Besides, it is really showing a really inaccurate, final grade because it's, a lot of points have not been accumulated yet. Alrighty. So that really gives you an idea of how the whole class did as in general, and I'm kind of surprised too. I was not expecting the class to be doing that well in general, so that's good. All right. Let's move on to your next homework assignment. Your next homework assignment is called Array 1. It is listed under topic number 7. So we'll just go take a look. You have 1 week to work on it, as usual. And the format is the same. You have to download a file and then work on it. So I'm gonna download the file just so that we can take a look at it and see if you guys have any questions about it. All right, so this is the algorithm of your homework assignment. I know it looks kind of long, but it's really not that bad. So we have a very usual, general structure. We start with, initializing I to 0. I is a very typical variable name that I use for indexing purposes. As long as I is less than something, an expression that is based on the number of elements in A, we will, do something. At the end of this loop, we have I gets I plus 1, just so that we can move on to the next item in the array. So that's a fairly, common structure in this class when we have to go examine items in an array, one by one. What is kind of interesting is what is in between. Okay, the in-between code, which is basically saying, what are we doing with each element in the array, looks like this. It is a conditional statement. It's comparing an array element to its neighbor. And if it is greater than its neighbor, on its right-hand side, then we'll do some assignment operations. Okay, we have 3 assignment operations to perform. Looks kind of nasty, but it's not. Okay, you just have to do it step by step and make sure that you understand when are we adding 1. Okay, we're adding 1 to I, and then what are we doing to the sum of I and 1? We're using that as an index. Okay, which is using it to tell me which element in the array we're dealing with. Okay. So it has most of the elements that we have talked about in this class. We are reading the value of something in an array. We're also overwriting the values of array elements. And you also have to rely on sheet 2. This is your starting point because I give you an array of 4 elements and they're already initialized. I and T are uninitialized because they will get their value while the algorithm executes. So that's your initial condition, and you have to finish this trace all the way to post, and that's your homework assignment for this week. Okay, there's only 1 trace, so it's not like I give you a lot of traces to do in this case. Are there any questions about this particular homework assignment? Now this algorithm is also a fairly useful algorithm. It is a part of what we call the bubble sort algorithm. This by itself doesn't do the entire sorting, but it is one important step of sorting an array. Okay. At this point, we're not going to talk about the bubble sort algorithm. We'll just do this part here, and then when we are done with this particular algorithm, then we can start to talk about sorting. But today, we're going to talk about searching. So before we even talk about sorting, we will talk about searching, which is finding a particular value in an array. Okay. And I'm going to turn editing on. And do you guys know that you can hide all of these things in Moodle? You can just click that symbol, so so you can hide all of that stuff. It doesn't work for me because once I turn on editing, add a block is always going to be there. But from your perspective, this can clean up the desktop quite a bit and give you more space if you want to do it that way. All right, so this is topic 7. We are pretty much done with topic 7. So we are ready to move on to topic 8 at this point, which talks about 2 things. The first one is short-circuited Boolean operators, And then the second one is how do we search in an array. The first one, short-circuited Boolean operators, is actually related to searching in an array that is not sorted. Okay, so that's the first thing we'll do today is to go through the algorithm that can search for items, but in an array that is not sorted. If an array is already sorted, we can do something a lot faster compared to this algorithm. So this is a good starting point to talk about short-circuited Boolean operators as well as searching within an array. And to start with this one, I'm going to start with, let me close the documents that I don't need. I'm going to close this one too, which is your homework assignment. And I will start another document just so that we can kind of figure out how do we search in general. All right, so this is going to be a spreadsheet. The first thing we want to do is to do it by hand first. Now, searching by hand is not easy to think about when you have a trivial example. I'll give you one trivial example, and then you guys can see what I mean when I say it's not going to help you, coming up with an algorithm. So I'll give you, the values inside an array. So the array itself is not actually spelled out here. These are just the values in the array. So I give you, let's say, 56, 31, 89, and 10, and then give you 101. Okay. So if I ask you, is the value 40 in this list or in this array? What do you think? 40 is not in the array. How did you know that? What algorithm did you go through in your mind to say 40 is not here? Did you use an algorithm? And how would you name that algorithm? It's called the eyeball algorithm. Okay, it's called the eyeball algorithm because it is not an algorithm. It's not a structured way because we can easily scan a few numbers and then say, okay, does any one of these numbers match 40? And we don't have to even look in a particular order. Okay, do you guys remember which order you used to search through this list? Was it top to bottom, bottom up, random? It doesn't even matter, right? Because there are only 5 items. So to understand, how to do this, but in a much more systematic way, this is not a good way to do it. Okay, this is too trivial as an example to, for us to even to think about, how to solve this problem. So to do this, maybe we should rely on something a little bit more lengthy, so that we actually have to think about it. So in this case, I'm going to use floor of random times 100, and we'll round it to units, like that. So right now I use a random number generator, and I'm going to generate 121 values. Okay, and I'm going to also change something about the screen here. I will use the feature like this so that I can scroll only one part and not the other part. And need to resize the screen, but I need to find that button. Okay, so I'm going to resize the screen to about this much. Now I will ask you to do exactly the same thing, and this time we are looking for the value 71. Okay. How would you do it? Okay, what can you do in this case to search for the value 71? You have the scroll control. Very good. Okay. So right now, we are comparing 55 to the value that we're looking for. I would even, print it out here. Okay, we're looking for 71, and we're looking for 71, and then the first value is 61. Is that what we're looking for? No. And then what do we do? Keep going, right? Scroll down. 15. Does it match 71? No. How about 16? No. 72. And we can do this all class long, and it's not going to be very helpful, right? But this is what you need to do, is to think about how to solve the problem, but from the perspective of your computer, okay, from your algorithm. Because your algorithm really cannot scan a whole bunch of numbers all at the same time. Okay? You can use an index to control which one you're looking at, but you cannot scan multiple items at the same time. Okay, so right now we are using an actual much more structured approach to do this. We are saying, okay, compare the number that we're looking for with an item in the array. It doesn't match, let's move on. Doesn't match, move on. So we'll keep doing this until we either find the item, and I'm not even sure that whether it's here or not. And there's no real check to this one because the array is not sorted. Oh, okay, we just found it, right? Okay, just by chance, okay, I found it. And so I have my conclusion and saying 71 is in the array. Should I look any further if the original question is, is there a 71 in the array? I do not need to look any further. Looking further may not hurt, okay, but it certainly is not needed. Great, okay, so that seems to be, something that would work. On the other hand, what if I change my mind and change the nature of the problem? Not knowing these numbers are confined to 0 to 99, I'm now looking for a number, let's say 132. Okay? If I'm looking for 132, obviously it's not going to be in the array because the array is initialized with numbers only going from 0 to 99. So in this case, how do I know when to stop? See? See, I keep going. Nothing is matching 132. Oh, maybe I should stop now. Why am I stopping? This is the last number, and then once I say, oh, 45 is not 132, move on to the next one. Why am I stopping now?
There's no more values.
There are no more values. The array, I have exhausted the entire array and still not be able to find the value 132. What tells me that I'm out of elements to compare? There are no values here, right? Okay. So it seems like now we have a much more structured approach to do it because the problem is now bigger, and I also confine your scope to just one item at a time. Okay, so the next thing we want to do is to come up with an algorithm to do exactly this, except it is going to be an algorithm, so at some point we can translate that into C, C++, or any programming language so that the computer can do it for us. All right. So let's go ahead and use mousepad for this purpose. Because we are deriving the algorithm, we are going to construct or synthesize the algorithm step by step. The first thing we want to know, you probably already know what I'm going to ask is, okay, let me just go all the way back. This is the first item. All right. So looking at this example here, do you think the approach, okay, I can actually display both at the same time just by resizing one to be here, okay. So do you think what we did was somewhat repetitive? Yeah, it's definitely repetitive, okay. So when something is repetitive, we know what type of control structure is in the program. Which type? A loop, okay, very good. Now when we just know there's a loop, we don't necessarily know whether it's a pre-checking loop or a post-checking loop. So I'll just use a generic name called loop and loop. Do you think this loop should exit at some point? If we implement it correctly, we should get out of the loop at some point. Okay, so we exit the loop. When what? When do we get out of this loop? It doesn't have to be very specific. You don't have to use arrays or concepts like that. Just tell me in general, how do we get out of a loop when it is supposed to find a particular value in an array?
How you equals n until you run out of stuff.
Okay, I like that. Go ahead.
When n equals x.
When n equals x. Okay, when some element in the array matches the value that we are looking for. Okay. All right. So let's go ahead and write this out, just the way it is. So I would just say when we can confirm the value, whatever the value is that we're looking for, is in the array or not. Okay. So I'll call this my first revision, even though it is awfully vague and doesn't even look like an algorithm at this point. Okay. Okay. Do you guys have any questions? No? Okay. Now, the next thing we want to do is to say, well, that looks really vague. Maybe we should make this a little bit more specific and use the disjunction operator the way it is supposed to be used. So we'll just go ahead and make this one a little bit more specific this time, and we say, well, the first condition is when we can confirm the value is in the array, and then we use the disjunction operator here, and then we say we can confirm the value is not in the array. Okay, we are just rewriting the original sentence a little bit more verbose. This is a more verbose format, but at the same time, it kind of fits our requirement a little bit better. Okay, are we doing okay so far with this code here? Okay, really vague, but it still describes what we need to do. Okay. In the next revision, I'm going to start to say, maybe we shouldn't really just say the value, okay, the value that we're looking for, or the array. Maybe we should use more specific names. So I'll just introduce the variables. We'll let variable k be the value that we are searching for, and then we use a to denote the array that we are where we are looking for the value. Okay. If that is the case, how do we rewrite this algorithm, knowing that we now have two variables, one is called k and one is called a. So we can confirm the value is k, is in a, and then here we have k is not in a. Okay, a is the array. Okay. That's a pretty direct translation. All we are doing is to save some typing in this case. All right. If you think about it, what does it mean when we say we can confirm k is in the array A? This is a really kind of really important jump here, so it's not necessarily an easy jump here. Okay. How do you confirm array A does contain an element that has the value k, using the notations that we have already introduced? Give it a try.
K is equal to A bracket I.
A bracket something, okay? Very good. Okay, A bracket something. Because when we say k equals A bracket, and we'll just use a question mark here because I don't quite know how to express it at this point, but I know it is an element in A. So when we use the square bracket operator, we are basically saying, oh, we're indexing into the array. Okay, we are specifying an element in array A, and in this comparison, all we're going to say is to say some element in A equals to k. That's all. Okay, but I'm not really quite sure, how to specify the question mark yet at this point. Okay. This one is a little bit harder, okay? Because to confirm that a particular value in array A equals to k is easy. One simple comparison can do it. But to confirm that k is not in A is a lot harder, because what you have to do is to say, I have examined everything, and they're all different from k. And in this class, we really lack the ability to express that. In a math class, you have the for all operator that can help you. But in this class, we are not a math class, so we don't quite have the means to express that just yet. Okay, so we'll kind of leave it the way it is, and then we move on. Okay, we look at the algorithm in this revision here, and one of the things that probably bugs everybody is the question mark. Okay, so how am I going to specify a particular element in A and compare that to k to confirm whether it is the same or not? Okay, should I use a constant in place of the question mark, something that does not change? Okay, we need some kind of variable, some kind of expression that can change depending on which iteration you're in. Okay, so whenever you have an idea like that, let's try something simple first. Okay, if the simple stuff doesn't work, then we'll work on something harder. So maybe we can just use a variable I to specify in this particular iteration which element we are examining, so that we can compare just that element to the value of k. Is that okay so far? So I'm going to say, okay, let's introduce a new variable. So let I determine which element in the array we examine for a particular iteration. Okay, a particular instance when we go through the loop. Are we doing okay so far? Okay. All right. That's helpful. I mean, introducing a new variable, and finally we have a little bit of a closure because now we know how to specify. We can now confirm that a particular element in the array is what we're looking for. Okay, but now we have a little bit of a problem. Two problems to be exact. One is where do we start? Okay, because now we are referring to the value of I and say it is going to help us determine which element that we should be looking at. So that's a read operation because we are just referring to the value of I. We are not setting the value of I. So that's one problem. The second problem is what are we doing to I for each iteration? What if k does not equal to a bracket I? What am I going to do in the next iteration? That's the question. So what do you think? Let's handle the second question first. The second question is actually the easier one. So we'll copy and paste the code here, and we want to specify what are we doing for each iteration. What do you think? Okay, let's go back to our example in the spreadsheet. Okay, we can see that 79 does not equal to 132. What are we doing next? We are moving on to the next item, right? And 89 does not equal to 132. We are moving on to the next one. So how do we accomplish something like that in this particular setting?
Add 1.
Just add 1 to I. Increment I for each iteration. All right, so we can do that. I gets I plus 1. And how about the initialization of I? We should probably start from the very beginning of the entire array. So we want the first element to compare to be the first element in the entire array. And the index of the first element is
0.
0. Very good. Okay, so maybe we should just say I get 0, and we have just about everything done here. We still have that one little nagging point of how can we confirm that k is not in the entire array A. That's a little bit harder to specify, but let's kind of think about it in our example. Okay, how did we confirm that 132 was not in the entire array? Now remember, even though I kind of rig it so that 132 cannot possibly be in the array, we cannot make that assumption. Okay, that's just one way for me to make sure that 132 is not in the array. So we keep going like this, and keeps going and going and going, and I think we have 120. Okay. All right. So now we are at the last item here. And boop. Okay, we have just gone past the end of the entire array. And since everything that we have seen does not match the value that we are looking for, and now we are at the very end of the entire array, I can now say, with certainty that the value is not in the array. So how do we express that in the algorithm? Okay, let's think about it. Okay, at this point in the example, let's think about the components that we need in order to make that determination. What do you guys think would be the necessary components?
K.
K.
I.
I is important. Okay, I is important here. What else do you think might be important to determine that we are now at the end of the entire array?
The number of elements in the array.
The number of elements in the array, that seems to be pretty important because if the array is longer, then we cannot quit with a smaller value of I. When the array is shorter, we can quit when I has a smaller value. So it does seem like bar A bar is important in this case. How do we work this out? I know some kind of comparison is required. Go ahead.
I is greater than the number of elements in A.
Okay, that's one portion of what we're looking for. Yep.
While I is less than the number of elements.
Well, when I is less than bar a bar, it means we haven't seen everything yet, right? Because when I is less than bar a bar, I is a valid index into the array. Sorry?
We're not determining yet whether it's supposed to be.
That's correct. But when we say exit when, that means we are specifying the exit condition and not the stay in loop condition. Yep, go ahead.
Would it be I plus 1 equals bar a bar?
I plus 1 equals bar a bar. We are pretty close. Go ahead. There are multiple ways to express it, but I have one in particular. Yep.
When I equals bar a bar.
When I equals bar a bar. Okay, when I equals bar a bar, we certainly can exit. Yep.
I is greater than bar a bar?
When I is greater than bar a bar, which was what you suggested, that's one step too late. What is the index? Yep, go ahead.
When I plus 1 is greater than bar a bar?
Yes, yeah, that would do it. So the answer is when I, but there are multiple ways to express the same thing, but I would say when I is greater than or equal to bar a bar, or I can say when I is greater than bar a bar minus 1. Okay, they're all expressing basically the same thing. The reason is, what is the index of the last element in any array? Let's call the array A. Okay, what is the index of the very last element in that particular array?
Whatever the value number in the array plus 1. Or less.
Minus 1. Okay, so the number of elements, which is bar a bar minus 1, is the index of the very last element in the array. Well, does it really work out? Well, there's a really easy way to check it out. Okay, what we want to do is to deal with a very small array, an array of only 2 elements. Okay, so in this case, bar a bar equals 2 because we have exactly 2 elements. How do we number these 2 items? We number the first one as 0. We number the second one as 1. Bar a bar, which is 2 minus 1, is 1. So it is the index of the last element in this case. So in general, that is the case as well. So the index of the last element in an array is bar a bar minus 1. Back to our algorithm. I only makes sense. I only want to do comparison when I is less than bar a bar, right? Because that's the only time when it has a valid value. On the other side, we know it's not going to be a negative value because we initialize I to 0, and the only thing we do to I is to increment it. So we know I can only be as small as 0, but it cannot be negative, right? Okay, so this is the correct code. Okay, but we're not done yet because we have to determine whether to use a pre-checking loop or a post-checking loop. What do you think? Okay, let's think about it this way. When I does equal to 0 because of the initialization, is that the value that we want to use for the comparison, or do we want to wait until I becomes 1, then we want to perform the first comparison? Do we want to wait until it becomes 1, or do we want to compare to a bracket 0? We want to compare to a bracket 0, so that kind of answers the question. Should it be a pre-checking loop or a post-checking loop? We want to check before adding 1 to it, so it's a pre-checking loop. Okay, so we'll go ahead and finish this up, and we'll say while k equals, when we use a pre-checking loop, we're going to specify the condition to stay in the loop and not the exit condition. So we have to flip the entire condition around to its negation. So that means while k is not a bracket I, and I is less than bar a bar, then we should stay in the loop, add 1 for each iteration, and that is my algorithm. Except this one doesn't work all the time. Okay, so in this class, I went through exactly the same exercise this morning. So in this class, we're going to talk about 3 versions of basically the same algorithm. We'll refer to these 3 as the bad, the good, the bad, and the ugly. Okay, this is the bad because it doesn't work. Okay, you look at this algorithm and say, how can this possibly not work? I mean, we spent all that time to derive the algorithm. Did we really overlook something? Well, the answer is yes, we did overlook something, and I'm going to use a trace to illustrate what we just overlooked. Go ahead and create a new spreadsheet, and just type in the algorithm the way it is, which is incorrect. So we'll say while k does not equal to a bracket I, and I is less than bar a bar, do the following. I guess I plus 1, and while, give it line numbers, and save this one as, okay, I'm going to save it to the temp folder. Okay, this is called bad. Okay, because it is not going to work. Not in all cases. All right, so now we'll give it some test cases. The first test case I'm going to give it is, they're all going to be simple test cases, but the first one is going to be like this. Okay, we have comments because we do have a condition to evaluate. We have line number, we have I, K, and array A. In this case, I'll just make array A really, really short. It has exactly 2 elements. I have to pre-initialize the array because otherwise I cannot compare to the elements. So I'm going to pre-initialize this to 1 and 7. And the value that I'm looking for, let's say we're looking for something that is in the array, just to see whether the array will exit at the right time. We'll call that 7. And I is not initialized to begin with. And we'll shrink the columns a little bit so we can see everything. There we go. All right. So this is my precondition, and I'm just using this to test the algorithm and see whether it works or not. All right, so let's go ahead and trace the algorithm. We start with line 1. I gets initialized to 0. We go to line 2. Now we have to evaluate these things. Okay, k is different from a bracket I. K has a value of what? 7. I has a value of 0. So a bracket I is referring to a bracket 0. A bracket 0 is column E. It has a value of 1. 7 is different from 1 is true. Okay, that's good. And the conjunction needs a second component, which is I is less than bar A bar. I is 0. Bar A bar in this case is 2 because we have 2 elements in the array. So I is less than 2 is true as well. So now we have true and true, which is true. Okay. And that means the next line that we have to execute is where? When the condition is true for a while loop, what do? We perform one iteration. Okay, so we go to line 3. Line 3 just adds 1 to I becomes 1. We go back to line 2, and now we have k, which is still 7. We compare that to a bracket I, but I is 1 this time, so we're comparing to a bracket 1, which has a value of 7. 7 is different from 7 is false. Okay, so we have one side determined. I is 1. 1 is less than 2 is true. So now we have false and true, which is false. Okay, and we get out of the loop. Everything is good. Okay. Okay. So let me answer your question. Okay, let me answer your question now. I was actually I saw your hand, but I needed to finish what I was talking about first.
I just missed what you were saying the bar represented in terms of the array. You're saying it's the array.
It's the number of elements in the array.
So the 0 position and the 1 position.
It's the number of elements in the array. So we have 2 elements in this case.
1 and 7.
No, we have 2 elements in this case. The values of the elements are 1 and 7 respectively, yes.
So what am I missing? Because I'm not understanding where the disconnect is. You're saying that because we're comparing this I is less than bar A bar, and bar A bar represents the 2 elements in the array.
No. Bar A bar does not represent the 2 elements. It represents the number of elements, which in this case is a 2.
And that's it, not the actual values in there.
Correct. It's a measurement measuring the number of items in the array, the number of items. All right, so it seems to work just fine. I mean, why am I so worried about this particular algorithm? Maybe we should try it with a second test case, right? In the second test case, we have, let's pick a value that we cannot find in the array. Okay, so we'll pick, let's say 3 in this case. Okay, I don't really have to erase everything, but that's fine. The first and second steps are pretty easy to track. Okay, so we start from the beginning again on line 1. Line 1 is initializing I to 0. Line 2, same thing. We are comparing k, which has a value of 3 this time, to a bracket I, but because I is 0, we are comparing to a bracket 0, which has a value of 1. 3 is different from 1 is true. Very good. And the other side of the conjunction is comparing I to bar a bar. I is 0, bar a bar is 2, 0 is less than 2 is true. So now we have true and true, which is true. Okay, so we move on to line 3. Line 3 is adding 1 to I. Same stuff as before. But this time when we get back to line 2, the condition is different from the last time, from the previous time. I should say the previous trace, because in the previous trace, the second iteration has this condition being false. So this time we have k being 3, different from a bracket I, because I is now 1. We're comparing to a bracket 1, which has a value of 7. 3 is different from 7 is true. Okay. I has a value of 1. 1 is less than 2 is true. So we have true and true, which means the entire thing is true again. Now we move on to line 3. We go to I is incremented from 1 to 2. We go back to line 2, and we have a problem pretty much right away, because right at this point here, okay, we have a problem. Because what is the value of I at this point? I has a value of 2, and where is a bracket 2? The array does not have a third element. Okay, so once again, when we get to this point, depending on which programming language you are using, they will respond differently. In Visual Basic, you get a runtime error right here, and it will complain and say on line 2 of this particular program, you're trying to access an array out of bound, and now you know where to fix it, or at least what is the immediate cause of the runtime error, which is the best way of handling something like this. C, on the other hand, will do what? We kind of talked about this on Tuesday. See if you guys can remember what C and C++ is going to do.
Overwrite the array?
No, well, in this case, we are not overwriting anything because a bracket something never appears on the left-hand side of an assignment. So we're not going to overwrite anything, but you're close.
Add a new
No, that's not C and C++. That's Perl, PHP.
It's going to read other places.
Exactly. It's going to read whatever is in column G in this case and say, I'm going to compare that to the value of k. It is still.
Finding it. It could end up finding the number you're looking
It can
for.
end up finding it, or it can end up not finding it, or if that is really the last byte or the last portion that you need to read, that you are allowed to read in memory, it can cause a segmentation fault. Okay, because you're trying to read past what your program is supposed to read. So all kinds of bad things can happen in this case, but none of that is right. Okay, they're all bad things. In Perl and PHP, it's even more nasty because the attempt to read an element that still does not exist will cause the interpreter to make it exist. So poof, a bracket 2 now exists with a some kind of initialized value, because all interpreters will give you an initial value, which is unlikely to be 3. So the inequality will still be true. So you will go on and on and on, because after each iteration, you will try to access an element that still does not exist. Poof, it starts to exist, and then your array just got a little bit bigger. Bar a bar is incremented, so the loop will never exit when you're doing this in Perl or PHP or most of the scripting languages. Are we doing okay so far? Okay. Yes. Does everybody understand what the problem is? We're trying to use I as an index when it is already out of range. All right. So how do we fix this problem? Where is my good.ods? Okay, so this is bad.ods. Let's go ahead and save it. Just so that we can compare the two algorithms later on, in this class. Now we save it as good. How am I going to fix this problem? I think I'm going to fix it like this. I will exchange the order of the two expressions of the conjunction, and I'm going to say, this is going to fix the problem. If there are any mathematicians in this class, the mathematicians will instantly jump up and say, but Tech, that cannot possibly do anything because conjunction is supposed to be commutative. Okay, just like multiplication or addition, it is commutative, which means exchanging the order of the operands or the two sides of the operator does not change the outcome. Then my response to that will be, well, that's why you're in a programming class. Because in programming, the order does matter, especially when you use what we call short-circuited evaluation, otherwise known as lazy evaluation. Okay, so let's see how laziness is going to save the day in this case. In general, it doesn't happen, but in this case, it does. So being lazy is going to change how things are actually done. All right, line 1, no big deal, same as before. Line 2, okay, so this time we're going to use short-circuited evaluation, which means we only evaluate as much as we need to get the value of an expression. Okay, let me say that again. Short-circuited evaluation means we only evaluate as much as we need to determine the outcome of an expression.
So I mean, if a false pops up first, the whole thing is false?
Yep. Then it doesn't even bother to evaluate the other side of the operator. Okay? Is that really going to save the day, even though it is more efficient, but is it going to change the program enough that we won't have a problem anymore? Well, let's take a look. In this case, we still evaluate I is less than bar A bar, but this time we evaluate it first. Okay? I is 0 at this point, bar A bar is 2, 0 is less than 2 is true. Can we now say, oh, the whole thing is going to be true and I'm all done? No, because it's a conjunction. What if the second part is false? The whole thing can still be false, right? So I cannot determine the entire outcome yet at this point. I have to evaluate the other side. K is different from A bracket I. K is 7. A bracket I is 1. K is 7 is different from 1 is also true. So now we have true and true, which gives us the result of true. We go to line 3. We increment I by 1. We go back to line 2. And it's basically the same thing. I is 1 in this case. 1 is less than 2 is true. K is 7. Is different from A bracket 1, which is also 7, is false. So now we have true and false, and then the result is false. Okay, and that makes me exit the loop. We're done. Hey, that doesn't seem to do a single thing compared to what we had before in bad.ods. What's the deal? Let's pick an example where it had a problem before and see whether it fixed this problem. Okay. So we'll start from scratch again, start on line 1, initialize I to 0, go to line 2. Okay, this part should be getting kind of boring at this point. I is 0, bar A bar is 2, I is 0 is less than 2 is true. I cannot yet determine the outcome of the entire conjunction, so I'm forced to evaluate the right-hand side. So in this case, we have K is different from A bracket I. K has a value of 3, A bracket 0 has a value of 1. 3 is different from 1 is true. We have true and true, so the end result is true. We move on to line 3, we add 1 to I, we go back to line 2. Okay, so let's see what happens this time. I is 1, 1 is less than 2 is true. Because this is a conjunction, I cannot yet determine the entire thing is going to be true. Let me finish this and then I'll answer your question. Now we compare K, which always has a value of 3. And compare that to A bracket I, which is A bracket 1, which is 7. 3 is different from 7 is also true, so now we have true and true, which is also true. And let me answer the question now. Yep.
Well, just in terms of this going through this loop, if this was not a loop and the first portion was false, can the second portion be just, you know, for lack of better terms, gobbledygook and not cause a runtime error? Because it's not even going to compare it against it?
That's because, well, we are going to, in the third iteration, that's going to happen. So we'll see what happens in the third iteration now that we're using short-circuited evaluation. Okay? So the answer of this one is true. We still have to move on to line 3. Yep, go ahead. Row sheet. Yep. Good reminder. And I have a brand spanking, new sheet, for this class. There we go. All right. So getting back to line 3, we are adding 1 to I. I goes from 1 to 2. We go back to line 2. Okay. So this is where the magic happens. Okay, because we are evaluating I is less than bar a bar first. What is I at this point? I has a value of 2. Bar a bar is 2. 2 is less than 2 is false. If I know one side of a conjunction is false, can I conclude the result of the entire conjunction? Yep. Okay. So using the principle of short-circuited evaluation, I can just conclude right now and say the entire expression is going to be false. Because the left-hand side is false, I don't even bother to evaluate the right-hand side. So the problem that I had in the previous pseudocode does not exist anymore because of short-circuited evaluation. Are we doing okay so far with this logic? And because it is false, it doesn't cause any problems, I'm going to exit the loop and get to the end of the program. And that's it. It's all finished. Are there any questions about this trace? Okay, I got a question. So who is determining that in which direction should we read the conjunction? Because if I read it from left to right, we can avoid the problem that we had earlier. But what if we read it from right to left? Don't we end up with the same problem again? Well, the answer to that is it is a part of the language specification. When it comes to logical operators like OR and AND, it is always evaluated from left to right. Okay, that is a part of the language specification, which means regardless of whether you're using Microsoft C++, C# or whatever C compiler that you're using, they all have to behave exactly the same way. The compiler cannot choose randomly and say, I want to evaluate from right to left or left to right. It has to be from left to right. Are we doing okay so far with that concept? Now, that assumption does not apply to anything else. If in your program you have something that looks like x times y, the compiler can choose to evaluate y first and then multiply that to x. Because short-circuited evaluation actually does not apply to multiplication. And somebody's going to say, but if this is 0, the whole thing is going to be 0. That is true, but as far as the compiler is concerned, it always evaluates both sides of the multiplication. In the case of a logical operator, it only evaluates the right-hand side if the left-hand side is not enough to conclude the result for the entire expression. Okay? Yep.
And that's in all cases, across all languages and everything?
Most languages that are still in use today use short-circuited evaluation. There are languages that are not like that. Okay, I believe Lisp may be one of those. COBOL is probably one of those. Fortran is one of those. And Pascal is probably the most modern language, still does not have short-circuited evaluation. But if you look at Visual Basic, Perl, PHP, Bash, most of the programming languages now have short-circuited evaluation. But that's a very good question. What if you don't know? Okay? What if you have a job and you have to write programs or fix programs that are written in a particular programming language that you're not familiar with, and you cannot see whether you cannot determine whether it uses short-circuited evaluation or not? What should you do? Should you assume that it has it, or should you assume that it does not have it? Which way is more? Which way is safer? Assume it doesn't. Okay, very good. So now that we have the bad and the good, we move on to the ugly. Okay? I can see from the lack of response that many people may not even know the movie. The good, the bad, and the ugly. I can see there's a certain age divide here. It's like, you know, a certain, on one side of the divide, it's like, what are you talking about? On the other side of the divide, it's like, yeah, I know what you're talking about. Okay, so now we'll save it again as ugly. Who is ugly in that movie? Ugly is neither good nor bad, right? In this case, ugly is correct, but not really good to look at. Okay, you know, it's definitely one of those things where, wow, you know, I don't want to deal with programs that look like this, but you do have to deal with it when a programming language does not have short-circuited evaluation. Okay, so now at this point we'll say, what if short-circuited evaluation is not in the programming language, or it cannot be assumed? What is the problem? What is the source of the problem here? The source of the problem is on line 2, where we try to do two things with one single line. We're trying to say, are we at the end of the entire array using the left-hand side? And also asking, are we looking at an element that has the same value as what we're looking for? Okay, we're trying to determine two things at once. And that's the problem, because you know, if we are already past the end of the array, the first condition being false, if we cannot avoid the evaluation on the right-hand side, then we have a problem. Okay, so that's why, you know, we have to keep these two expressions away from each other. They cannot be on the same line, or they cannot be a part of the same expression. So we have to kind of decouple these two and say we can only have one at a time. But if I only have one at a time, then how am I going to exit early if I do find the element that I'm looking for? What you can do is to say, okay, we introduce another variable here. We introduce a variable to keep track of, have we found the element or the value that we are looking for? The assumption is false, okay? The assumption is we have not found it yet, okay? And then we also have to change the code here to include a line to update found. Found is going to be just a bracket I compared to the value that we're looking for, like that. Okay, so this is ugly because, you know, we have to introduce another variable to track, have we found the value that we're looking for? And it is also kind of cumbersome, okay, because you can see that this program is a bit longer, and the complexity, there are more logic that we have to specify. But the question is it going to work? Does ugly get to live at the end of the movie? I know someone's gonna, you know, go to YouTube tonight and go, okay, I need to find out what he's talking about. All right. And by the way, that movie was not filmed in the United States, even though it's a cowboy western movie. Where was it filmed?
Italy.
Yep, and therefore there's a term for that entire genre.
Spaghetti westerns.
Yep, spaghetti western. Yep. The same country that made Ferraris, you know, also made spaghetti western.
It's a good movie.
It is a good movie, classic. All right, so we'll go ahead and trace this algorithm and see whether it works or not. All right, so we'll need one more column here because we have one more variable in this case. So we have found, and I think the other ones I can make them a little bit narrower. These two, a little bit narrower. This one maybe a little bit, or I can just increase the magnification. Okay, now we can see everything. All right. So we start with line 1 again. Okay, that's kind of boring. Line 2, kind of boring because, you know, we can definitely store a value of false in a variable. We talked about this last time, right? Because we look at an assignment statement. What is the job of an assignment statement? It evaluates the right-hand side, get a value of some kind, and then store that in the variable specified on the left-hand side. In this case, the value on the right-hand side is false. False is just as good as a value as 0, 1, or whatever. And on the other side, we have variable found, which has its own column, column E, so we can definitely store that value. So there's no problem with this step here. So we move on to line 3. Line 3 this time is going to evaluate same as before. I is less than bar A bar, which we know is true because 0 is less than 2. It's also going to evaluate not found. Not found actually sounds just kind of natural too. But in this case, found is the name of a variable. What is the value of that variable at this point? False. What is not false? True. So now we have true and true, which is true. Okay, well that's not too bad. Okay. And then we move on to line 4. How do you think we're going to update line 4 update found in this case? Can that really be done? I mean, is the right-hand side really specifying something that has a value?
True.
It's true, exactly. Okay. In this case, I has a value of 0, right? And A bracket 0 has a value of 1. Can I compare 1 to another value, like 3? Sure, okay. 1 equals 3 is false. Is that a value? Yeah, and I can store that value in found. Okay, well, that's good. So found is getting updated, quote unquote updated, to a new value of false. And we move on to line 5. We add 1 to I. We go back to line 3. Same thing, because I is 1 in this case. 1 is less than 2 is true. Found is still false, so not found is true. True and true is once again true. We go to line 4, and this time we are evaluating on the right-hand side, A bracket I equals K again, except I, in this case, is 1. A bracket I is A bracket 1. A bracket 1 has a value of 7. 7 equals 3 is false, so we're going to update found exactly the way it is. And then we go to line 5, we add 1 to I. I goes from it goes from 1 to 2. So at this point, I is no longer a valid index into the array. Are we going to have a problem on line 3? No, because line 3 has no indexing operator anymore. So even though I is no longer a valid index into the array, line 3, or the condition of the loop, is not bothered because it doesn't refer to any element in the array. That's why the problem is solved. So in this case, I is 2, 2 is less than 2 is false, and because we are not using short-circuited evaluation, we have to keep going. So we have to say, what is found? Found is false, not found is true, so now we have false and true, which is false, so we still have to exit at this point, get to post, but this time it doesn't crash. It doesn't crash, and yet we are not relying on short-circuited evaluation. Are we doing okay so far? Great, we solved one problem. But is it possible that in solving one problem, we are introducing another problem?
Yes.
Okay, it's entirely possible. Okay, according to IBM, in some cases, the average bugs introduced while fixing another bug was greater than 1. In other words, it's better not to fix the bug because by fixing a bug, the chances of introducing another bug is high, is almost certain.
What article was that?
I cannot remember, but since it was quoted so many times, it's almost like geek legend now. So let me find it. IBM bugs ratio maybe. Okay, let's see if I can find it like that. That's a little hard to search because it has a
Bugs cause fixing bugs or something.
okay.
Put it like
Bugs
rational or something
lead
like that?
to
More
bugs. Oh, more is a good word to use. Okay. No more bugs in your beans. That's Java beans, by the way. Okay, I cannot find the reference, but it was rumored. Okay, it was rumored as geek legend that somebody found that when you're fixing a bug, the chance you can introduce more bugs in the process. I think it's true for certain people, and that's why some employees, if you cannot fire the employee, it's better to just tell the employee to stay home instead of working. It's like, Tom, please stay home. But I want to work. No, it's okay. We got it covered. Because when Tom works, he would introduce more bugs in the process. It's like, nope, don't touch my code. Unfortunately, I have met people like that. And because of where they work, they cannot be fired. So the best way is to say, oh, there's another way to solve that problem. Promote Tom to management. Where he cannot do as much harm. I have seen that too. I know some of you are thinking, maybe we should make Tom a teacher. Well, that's what they say, right? I mean, if you can, you do. If you cannot, you teach, right? That's a.
Not why you're here?
Hmm?
Not why you're here?
No, the reason I'm here is because I enjoy my 30% pay cut in this job, by switching to this job. All right, so, but we are not done yet, okay? Because this is only one test case. We should try out the other test case too, because just to make sure that we did not introduce a problem by fixing another problem. Okay, so let's go ahead and trace this one and see whether ugly is going to get this right too. All right, so let's go ahead and give it a shot. And then we'll also have one more test case by exchanging the 1 and the 7, because we want to see whether it can catch it early on and be able to exit early on too. Okay, so we'll start with line 1, that's a 0, line 2. Oh, we have to introduce a new column, so we'll go ahead and insert this. Found here. Nope. Found starts with a value of false. And then we move on to line 3. I is less than bar, a bar is true, 0 is less than 2. Not found is true because found is false, so not found is true. We move on to line 4. Found is a bracket I gets k, equals k. A bracket I is a bracket 0 has a value of 1, k has a value of 7, so it is false. The equality is false. We go to line 5, we add 1 to I goes from 0 to 1. We go back to line 3, I is less than bar a bar is true because I is 1, bar a bar is 2, and not found is also true because found itself is false, not false is true. So true and true is still true. We go on to line 4. But this time a bracket I, which is a bracket 1, equals k is true because they're both 7. So now we have value of true in found. We move on to line 5. We add 1 to I goes from 1 to 2. We go back to line 3. And on line 3, because we are assuming we don't have short circuit evaluation, so I is less than bar a bar is already false. But because we are assuming there's no short circuit evaluation, we have to keep going. Okay, we have to evaluate the other side of the conjunction. Found is true in this case, so not found is false. Now we have false and false, which is false. And we get out of the loop. And not only that, the variable found also has the answer that we are seeking, which is basically saying, yes, that particular value is in the array in this case. This is good. But we need to make sure that it will also work in one last test case, which is having 7 first and 1 second. So this way I can check whether the algorithm is going to exit early, after finding the first 7 and just say, okay, we don't need to look at the rest of the array here. And this time I'll just be a little bit lazy and not start all the way from scratch. Okay. So now we are on line 3. I is 0. Bar a bar is 2. 0 is less than 2 is true. Look at the second one, found is false, not found is true. So now we have true and true, which is true. We go to line 4. Hey, this time we found the value in the first iteration because a bracket 0 has a value of 7. 7 equals 7 is true. So, okay, it is true already. We go to line 5, we add 1 to I. We go back to line 3. I is 1. 1 is less than bar a bar is true. But found in this case is already true. Not found is false. True and false is false. We get out of the loop, and we have the right conclusion in the variable called found. And this is why ugly works. Okay? It is ugly. I mean, if you look at the code, it definitely is not clean like the other one. But it does work. So if you have any opportunity to work on, let's say, COBOL or Fortran, one of those older but practical programming languages, and you cannot make any assumption, it may have that feature, okay? Because a lot of the older languages have newer versions that actually implement short-circuited evaluation. But if you cannot make an assumption, this is the safer way to go, okay? Because this code will work just fine with short-circuited evaluation as well. So it's a safer, assumption, and just say, okay, let's assume it does not have short-circuited evaluation. Yep, go ahead.
Are there any drawbacks to short-circuited, or is it just always a good way to go?
It makes code analysis actually harder in many cases. We cannot see it now because we have not introduced the concept of subroutines. Now, if you have subroutines that returns a Boolean, then we have a potential problem because by invoking the subroutine, it can have side effects, right? And if the conjunction is short-circuited, that means it is not going to call the subroutine every single time. And that makes the analysis of that type of program a little bit more tricky because you can't, by reading that line, it is not clear that sometimes we do it and other times we don't do it. If you say if blah, 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 then invoke the subroutine, then it's really clear that we only execute the subroutine sometimes. But when you put it in a conjunction, then it's not clear that that's the case. So we won't see it at this point because we have not really talked about subroutines and the side effect of subroutines yet. But by the time we get there, we can kind of mention this again. Okay, so we are pretty much done with short-circuited evaluation because I gave you the reason why we have it, why it fixed the problem that we experienced in the first place, and what if we don't have it? How do we fix that problem? So we have talked about all of those things in today's lecture. One thing, so it's time to kind of move on to talk about how do we do searching in a sorted array. So we are now moving on to here, and before we go any further, I'll go ahead and fix it so that the link works. Because when I upgraded Moodle to a newer version, it broke all of the links. And then we have this one to fix, the second one. Let's see. Oh, this one is fixed already. Maybe not in frame. We'll make it. Okay. And then I'll double check it test them first. Yep, that works. And then check the second one and make sure that works too. Okay, they both work. All right. And we only have about 7 minutes left, which is plenty of time to talk about binary search. Okay, binary search is one of those really kind of fun algorithm that really changes the way we look at things, kind of fundamentally. So let's say we have a directory of the entire population on Earth of humans. Okay, what is the current population, human population? 7 billion or something. Okay, so we have it's less than 8. Okay, so if I give you a huge directory of every living person, okay, it can be sorted by something. Okay, maybe name, ID, or whatever. Okay, it doesn't matter. And it is sorted by some kind of criteria. I'm giving you a key, a particular value, and I say, okay, go through this entire huge long list with 7 plus something billion items, and tell me whether this entry is in the array or not. Is this person alive or not? Okay. How many comparisons do you think you will need? 7 billion comparisons. But that would almost for sure whether to confirm, especially when this person is not in the database, you will need to go through the entire thing to find out, right? What if I tell you this array is already sorted? In the worst case, it will still be 7 billion items because it's possible the key is higher or larger than all of the values already stored. So you still have to go through the entire thing in order to confirm that this particular item is not in the array. What if I tell you I can do it in 33 comparisons to confirm that something is not in the array, so it's not a lucky shot? 33. Now, how do I come up with the number 33? Well, let's think about this. 2 to the power of 33 is what? Okay, well, nobody's whipping out a calculator. All of you were whipping out your smartphone earlier to check your grade a little bit earlier, and then when I ask you an arithmetic question, nobody cares. It's like, whatever.
8 million.
Okay, there's a quick and easy way to do this. Okay, the quick and easy way to do this is to break it down to 2 to the power of 10, and then we have one remaining portion, which is 2 to the power of 3. Okay, now why do I want to deal with this? Well, that's because 2 to the power of 10 is, well, I should say exactly 1024, which is approximately 1,000. For estimate purposes, this is good enough. So now we have 3 of these things, so we have 9 zeros times the 8 here. 2 to the power of 3 is 8. So this number is approximately 8 billion. Sorry?
8.6 billion.
8.6 billion, but for the purpose of estimation, this is okay. Okay, so it seems like this 33 has something to do with that. Well, that's because binary search is doing something that's really, really smart. You give me a deck of cards that is already sorted. You give me a value that you're looking for. What I'm going to do is I'm not starting from the beginning. I'm not starting from the end. I'm starting from right in the middle. I pull out one card from the middle of the stack, and remember the location of where I pull that card out. If it doesn't match, it can only be one of 2 cases, right? Because if the card doesn't match the value that you gave me, it's either larger than or smaller than. Am I making any sense here? Okay, now I can guarantee it has to be ordered because otherwise sorting does not make any sense. You can only sort values that can be ordered. Okay, so what is that going to do to me? I mean, okay, great. We have a huge stack of cards, okay? I pick one thing in the middle to compare to. You give me a particular value k, and let's say, this is the small values over here. These are the large values down here. So it is sorted in a non-decreasing, order. If k is greater than this value right in the middle here, what can you imply? Yep.
That's somewhere in the lower half of the list. Or upper half, sorry.
Okay, if k is larger than this value is greater than or equal to the value here, which is greater than the value here. So which half of the stack can you eliminate? The entire top half. Okay. So by one single comparison, I can eliminate the first half of the array containing the value of k, including the card that I just compared. Is that making any sense? What do I do next? Yep, exactly. The remaining portion, I pick the middle one to compare, and that will give me an indication which half to get rid of, right? Let's say I get rid of this half the second time. Now I have this much left. Make another comparison. So let's say this is the half that I can eliminate. I only have this much left, and make another comparison. So each time I compare, I eliminate one half of the possibilities left. And that's why it works out like this. Okay? in 33 comparisons, I can locate a single item or confirm it does not exist in about 8 billion entries. That is binary search. Okay, it's called binary search because we are dividing something in half. Okay, so it has only 2 ways to go. Okay, we have 1 minute left, so I'll just give you a preview of what I'll be talking about on Tuesday. It's called time complexity, and I'll give you a little reason why I will talk about that. So let's say I'm working for a software company. It is downsizing. It's down to me and Pat, okay, as the only 2 employees left as software engineers. And the company decided that it has to downsize to exactly 1 software engineer, so it's between Pat and me. The boss says we'll have a little programming competition, okay? And the programming competition is to implement a search algorithm so whoever comes up with the answer faster gets to keep the job, okay? But the boss is not interested in the number of comparisons. The boss, not knowing anything about computer science, is saying, in real time, if I clock you, if you can give me the answer first, you get to stay. Now, me being the old timer is using an old 386 SX computer running at a whopping 16 megahertz. Pat, on the other hand, joined the company last year, so he's running an i7 quad core, and is running at 2 point something gigahertz. Maybe he or she did something to supercharge it too. Okay, so it seems like I'm at a really bad disadvantage here, right? The computer that I'm using is probably thousands of times slower than Pat's. So do I have a chance to win in this case and stay in the company and keep using my the 386 SX computer? Or maybe get Pat's computer because Pat is getting fired, right? Okay, so that's the question, okay? The answer is yes, because if Pat is not careful and choose the wrong algorithm, okay, all I have to do is to say, boss, let's make the problem bigger. The tag, you're still losing, make it bigger. You're still losing, make it bigger. You're still losing, make it even bigger. Oh, you're starting to gain. Pat is saying, okay, I want to quit now, let's stop now. No, let's make it even bigger. And then at some point, I'm gonna win. Okay, that's why the time complexity issue is important, because at some point, maybe you'll be in my shoes and have to figure out a smart way to win in this kind of situation. Okay, the high-tech industry is cyclic. You can count on downsizing to happen again. Okay, so I'll see you guys on Tuesday, and have a nice weekend.